Okay, we're going to learn about a new type of function, logistics models. So this is like an exponential function. See, we start off like an exponential function, but then as we get, the part of the arm where it increases without bound doesn't exist in a logistics function. What happens is that the arm starts to level out, so we have what we call a carrying capacity. So we use a logistics model when we're talking about like the spread of disease or population growth, where both of these have like a cap. So the disease can only affect a certain number of people, and then it's just going to kind of cap out. So our equation is right here: a over 1 plus b times e to the rx. A is your carrying capacity, or the maximum value, the limiting value. R is the growth rate, and A over 1 plus B is equal to the initial value. All right, so another fun fact is that this midpoint right here would be like your carrying capacity over 2, and that's always your ln of A over B. All right, on a college campus of 5,000 students, one student returns from vacation with a contagious flu. What a jerk. The spread of the virus is modeled by y is equal to 5,000 over 1 plus 4,999 e to the negative 0.8t, where t is greater than or equal to 0. Also, y is the total number of infected after t days. So the college will close after 40% or more of its students are infected. So how many students are infected after 5 days? Okay, how could we do that? For part A, we can, 5 days is equal to our t value. So we're just going to substitute it in for t. Over 1 plus 4,999 e to the negative 0.8 times 5. And when I plug that in, I get that is about equal to 54.019 students. So we're going to round that down to 54 students. Okay. Next, for part B, how many days will the college, so after how many days will the college be closed? And remember, it's 40% of our students infected. So think about, what is our carrying capacity? So what is the top value for carrying capacity? Look at the equation. The numerator here is our A value. So we're going to have a carrying capacity of 5,000. So 40% of 5,000 would equal 2,000. Okay. So we need to figure out, so 2,000 is going to be our Y value. So we're going to plug it in. 2,000 is equal to 5,000 over 1 plus 4,999 e to the negative 0.8 t. All right, time to solve. I'm going to go ahead and multiply both sides by the denominator. And this side. 99 e to the negative 0.8 t. Okay. And so I get 2,000 is equal to, that's weird. 2,000 times 1 plus 4,999 e to the negative 0.8 t is equal to 5,000. And then divide by 2,000. Then we're going to subtract 1 from both sides. So I get 4,999 e to the negative 0.8 t is equal to 2.5 minus 1, basically, which is 1.5. Divide that by 4,999 to get the exponent by the exponential by itself. I'm going to go ahead and leave this as 1.9 times 4,999. And then, how do we get the exponent out? Well, we're going to take the ln. ln of e, so I'm going to put negative 0.8t is equal to ln of e, because it's going to go towards the front when I take the ln of both sides. And ln of 1.5 over 4,999. That 1.5 over 4,999 is the input. ln of e is equal to 1. So now I'm going to divide by negative 0.8. So I get, let me go this way. T is equal to the ln of 1.5 over 4,999 over negative 0.8, which is about equal to 10.1, 39 days. Okay, I'm going to double check that in my calculator. ln of 1.5 over 4,999 divided by negative 0.8. Yeah, that's a 3. All right, and that's it for that one. Okay, lastly, we're going to look at logarithmic models. So logarithmic models are like when we model earthquakes, or when we model sound intensity, or in chem, when you model the acidity. Okay, so these are all logarithmic models. So we're going to use this formula, a plus b times the ln of x, and we all know that a is the vertical shift and b is the vertical stretch factor. Our graph looks something like this guy over here. And so we have a Richter scale equation. R is equal to the log of I over I sub naught. I is the intensity of the earthquake, and I sub naught is the minimum intensity that we compare it to, so it's 1. So we're going to find the intensity of each earthquake. Let's start with A. It says that the Richter scale reading was 6.0, so we want to figure out what the intensity is. So for the R, we're going to plug it in. And, I sub naught is just equal to 1. So this is 6.0 is equal to the log of I. And then we're going to go ahead and snail this. So we get 10 to the 6th is equal to I, which is 1 million sound intensities. Okay. And then, or the wave intensity, excuse me. Okay, so B, we're going to plug in 7.9 for R. So we get log of I over 1. So I'm, again, going to snail this. 10 to the 7.9 is equal to I. And that is equal to, I is equal to 79,400,000. Okay. Lastly, we're going to look at C. So how many times greater was the intensity of the Eastern Szechuan earthquake than the Nevada earthquake? So we can take our intensities and divide them. So we'll take the Szechuan to the Nevada earthquake. So 79,400,000 all over 1 million is equal to 79.4 times greater. So even though the values are only 1.9 units of 1.9, it's actually 79 times greater than the Nevada earthquake. And that is that.